Hi everyone. Today we're continuing our discussion on Chapter 14, Chemical Kinetics. So today we're going to talk about integrated rate laws. Integrated rate laws are a little bit different from the rate laws that we saw last time. So a rate law shows the relationship between rate and concentration. And of course, it is useful to have an equation relating concentration with time. Now, using calculus, we can obtain the integrated rate law, and this shows the relationship between the concentration of our reactant, A, and the time of the reaction. Let's see, so another term that we need to know before we kind of dive into these integrated rate laws is the half-life of a reaction. The half-life, we're going to give the symbol T 1/2, and the half-life of a reaction is the time required for the concentration of the reactant to fall to half of its initial value. So, for example, if you have, let's say, an initial concentration of A that's equal to 0.1 moles per liter, half of that would be 0.05 moles per liter. And then the half-life is how long it takes to go from the initial concentration to the final concentration there. Now, the half-life of a reaction does depend on the order of the reaction. So we'll go through each of the orders we talked about last time, and we'll derive not only the integrated rate law, but also the half-life expression for each of those. So for a zero-order reaction, a first-order reaction, and a second-order reaction. So let's start with zero-order reactions. So in a zero-order reaction, remember that the rate law tells us that the rate is equal to a rate constant times the concentration of our reactant to the power of 0. So essentially, the concentration of A cancels out, and the rate is just equal to K. Because remember, anything raised to the power of 0 is just equal to 1. So we actually have constant rate reactions here. Now, you'll notice that we have an expression here where the concentration of A, our reactant, is equal to the negative of the rate constant times time plus the initial concentration of the reactant. Now, this comes from an integration. So remember that rate also is equal to the negative change in concentration of a reactant over a change in time. So we have our rate law, and then we also have our rate expression there. So we're going to set those to equal to each other. And I'll do that down below. All right, so in order to derive that expression we just went over, we need to integrate both sides of this equation. But I'm going to rewrite this as dA, so the change in the concentration of A, is equal to K times dt. And now we're going to integrate both sides. Oh, I forgot a negative sign in front of K. I moved the negative over. And this is just to make the integration easier. So I'm going to integrate from an initial concentration of A, which we'll label with a subscript 0, and then some other concentration of A, so a final concentration. And then I'm going to integrate over on the right-hand side dt from 0 to some time t. All right, so what this will give us is an expression where we have a concentration of A, so our final concentration minus an initial concentration of A. And then that will be equal to negative K times the difference in a final time t minus an initial time 0. So really, the right-hand side of the equation just simplifies to kt, because we're just going to subtract by 0 there. And then we're going to rearrange so that we have an expression for the concentration of A. All right, so that gives us the same expression we saw above. Now, if you haven't taken calculus, or if you haven't gotten this far in calculus yet, don't worry, you don't have to know how to integrate these equations, but you will have to know this final expression, which is our integrated rate law. Okay, now let's also derive the half-life expression. All right, so you'll notice that we have T1/2 is equal to the initial concentration of A divided by 2K. All right, so let's rewrite our integrated rate law. And again, this is for a zero-order reaction. And let's say that the concentration of A has decreased to half of its original concentration. So let's plug in 1/2 of the original concentration for A. And then we'll set that equal to negative K times T1/2 plus the concentration of A initially. So we're just substituting in some expressions, assuming that we have lost half of our initial amount of A. Okay, so now let's rearrange this equation to solve for T1/2. So I'm going to move the initial concentration of A over to the left. So essentially on the left-hand side, we have 1/2 minus 1. So what is 1/2 minus 1? So that'll give us negative 1/2 of our initial concentration, which is equal to negative K T1/2. And then if we solve for T1/2, our negatives will cancel, so it becomes positive. But then we'll also end up with our initial concentration of A over 2 times K. And again, you don't have to know how to derive this, but sometimes it's nice to see where these equations are coming from. So if we wanted to solve for the half-life of a zero-order reaction, we would use this expression. All right, now also on the right-hand side is a graph for a zero-order reaction. And one thing to notice is if we write out our integrated rate law for a zero order reaction, you'll notice that it's in the form of y equals mx plus b. So if we plot the concentration of A, which is our y value, versus T, which is the x value, we'll end up with a linear line, so a linear slope, I should say. And that means that the slope of this line is equal to negative k. So one way that we could determine what the rate constant of a reaction is, we could just plot the concentration as a function of time for a zero order reaction, and that will give us the slope, or our rate constant, negative k. So m is equal to negative k. All right, so now let's talk about first order reactions. Oh, if it will let me. Apparently I can't change the slide. Here, let me back out and we'll go to the next slide. There we go. Okay, so let's talk about first order reactions. Now, remember, for a first order reaction, the rate law tells us that the rate is equal to a rate constant times the concentration of A raised to the power of 1. So we can simplify that as just K times the concentration of A. Now, the integrated rate law tells us that the natural log of the concentration of A is equal to the negative of the rate constant times time plus the natural log of the initial concentration of A. So again, this is coming from the integration of our rate law. So let me find my notes really quickly. So remember, the rate is also equal to negative delta A over delta T. So the change in concentration over time. So again, we can set those two things equal. So the negative delta A over delta T is equal to K times the concentration of A. And then we can rearrange this equation slightly. So I'm going to write 1 over the concentration of A. So I'm just moving the concentration of A on the right over to the left. So I have to divide both sides by that. And I'm going to rewrite delta A as dA. And then we'll set that equal to negative K dt. And then we're going to integrate both sides. So we'll integrate again from the initial concentration of A to a final concentration. And then on the right-hand side, we'll integrate from time 0 to time t. And the integral of 1 over A, or 1 over x, if you like to think of it that way, is the natural log of A, or x. So we'll end up with the natural log of A minus the natural log of the initial concentration of A is equal to negative kt. And then if we rearrange to isolate the concentration of A, we get the expression shown up above. where the natural log of A is equal to negative kT plus the natural log of the initial concentration of A. All right. So now what about the half-life? And the half-life expression isn't written here on this slide, but the half-life, we're just going to find that the same way that we found the previous zero-order half-life expression. So I'm going to rewrite the integrated rate law, but I'm going to rearrange it slightly. So I'm going to move both natural logs to one side. And then we'll set that equal to negative kT. And now I'm just going to plug in the concentration of A after we've lost half of it. So we'll just substitute in 1/2 of the initial concentration of A. And then we'll set all of this equal to negative K times T 1/2. So what ends up happening here is the initial concentration of A cancels, and we end up with the natural log of 1/2. So if we plug that into our calculators, the natural log of 1/2 is negative 0.693. And that's still equal to negative K times T 1/2. So if we rearrange to solve for T 1/2, that will equal 0.693 over K. So what this tells us is that the half-life of a first-order reaction does not depend on the concentration of A. So for instance, if we go back to our zero-order reaction, the half-life does depend on the initial concentration of A. So you can see that at the very bottom. But for a first-order reaction, it's constant. So T 1/2 does depend on the rate constant, but it does not depend on the initial concentration of A. So that makes it kind of unique in that sense. Oh. So you'll notice here that down below we have a graph of concentration of our reactant versus time. So concentration is on the y-axis, time is on the x-axis. And let's say that initially we have a concentration of 1 mole per liter of our reactant. Now after one half-life, which is about 100 seconds, we'll have 0.5 moles per liter of our reactant. And then after another 100 seconds, we end up with 0.25 moles per liter, and the trend continues. And again, this half-life of 100 seconds does not depend on the initial concentration of the reaction. Oh, actually, I'm going to go back here to our first order reaction again. So if we look at our integrated rate law, you'll notice again that it's in the form of y equals mx plus b. So if we plot the natural log of the concentration of A versus time, that's going to give us a straight line. And from that line, well, we would hope it would be a straight line, right? But from that line, we should end up with our slope, negative k. And that's one way, of course, that we can find the rate constant for a reaction. All right, last but not least, second order reactions. So for this reaction, again, we can find the integrated rate law by the fact that the rate is equal to a rate constant times the concentration of A squared. But additionally, the rate, again, is equal to the change in concentration of A over the change in time, and that is negative. So if we set those two equal to each other, so those two rate expressions, oh, actually, let me do it the other way. Started with the wrong side. Now we can rearrange this equation, take the integral, and we'll end up with our integrated rate law. So this is a little more complex. If we rearrange this, we end up with 1 over the concentration of A squared times dA. And then we'll set that equal to negative K times dt there. And we're going to integrate both sides again. And you might recall from your calculus class that the integral of 1 over x squared is equal to x raised to the n plus 1 over n plus 1, and then plus some constant. So we're going to do the same thing here with our a 1 over a squared. So let me just erase this here. Okay, so what we'll end up with is the concentration of A raised to the negative 2 plus 1 all over negative 2 plus 1. So that equals the concentration of A to the negative 1 over negative 1. So really what we have is negative 1 over the concentration of A. Now we are integrating from an initial concentration to a final concentration. So we're actually going to take the difference in the initial or in the final versus the initial. All right, so let's rewrite that on the next slide. So we'll have, let me see, so negative 1 over the final concentration of A minus negative 1 over the initial concentration of A. And then that will equal negative KT. So let's simplify this a little bit. So we've got negative 1 over the concentration of A plus 1 over the concentration of A initial. And then I'm going to move the initial concentration over to the right. So we have negative 1 over the concentration of A is equal to negative KT minus 1 over the concentration of A initial. Now you'll notice that everything is negative, so what we can do is multiply both sides by negative 1, and then that just makes everything positive. And that's how we end up with our integrated rate law. So again, you don't have to know how to integrate these rate laws to get our integrated rate law, but sometimes it's just nice to see where these equations are coming from. Okay, so now let's derive the half-life expression. So again, if we rewrite the integrated rate law, we can substitute in the concentration of A at the half-life point. So that would be 1/2 of the initial concentration of A. And then for T, we'll plug in T 1/2. Okay, so then let's simplify the left-hand side of the equation. So if 1/2 is in the denominator, we actually have 2 over the concentration of A at its initial point. And then let's subtract the 1 over A expression. So 2 minus 1 is 1. So we have 1 over the concentration of A at its initial point. And that's equal to K times T 1/2. So that tells us that T 1/2 is equal to 1 over K times the initial concentration of A. So remember that we said that for a first order reaction, the half-life does not depend on the concentration of A, but for a zero order reaction and for a second order reaction, the half-life does depend on the concentration of A. Now, you'll also notice from the integrated rate law that it is written in the form y equals mx plus b. So if we plot 1 over the concentration of A versus time, we'll have a positive slope this time. So the concentration there is increasing linearly, or 1 over the concentration is increasing linearly with time. So for a second order reaction, the slope is equal to the rate constant. Okay, so if we're trying to determine the rate law for a reaction where A is becoming products, we can plot the concentration of A versus time, and then plot the natural log of the concentration of A versus time, and then also plot 1 over the concentration of A versus time. And this will allow us to determine whether we have a zero order reaction, a first order reaction, or a second order reaction. So whichever plot gives us a straight line, that will be the order of our reaction. So if we find that we have a linear plot when the concentration of A is plotted versus time, that means that the rate is equal to K times the concentration of A to the power of 0. If our plot is linear when we plot the natural log of A versus time, then our rate is first order. And if we have a linear plot when 1 over A versus time is graphed, then we have a second order reaction. So let's go over a couple of example problems just to really, see how this works. But also in your textbook, there's a really nice table, table 14.2, and this summarizes everything that we talked about today. So you have your order of reaction on the left-hand side, And then next to that is the rate law. Also listed in this table are the units of K, which is really handy, and they'll be different for each type of reaction. And then the integrated rate law is listed next to that. And then they also show the straight line plot for each and the half-life expression for each. Now, I can also make some online flashcards for you if that helps you learn the material better. And it will kind of guide you through what is the rate law, what is the integrated rate law, and what is the half-life expression for each of these different orders of reaction. All right, so let's go over an example. So let's consider the equation for the decomposition of SO2Cl2. So the concentration of SO2Cl2 is monitored at a fixed temperature as a function of time during the decomposition reaction, and the following data are tabulated. So we have time 0 and our initial concentration of our reactant. And then after every 100 seconds, the concentration is recorded. So we want to show that the reaction is first order, and we want to determine the rate constant for the reaction. So remember that is K. All right, so if we want to prove that this reaction is first order, let's go back to our table. That means that we want to plot the natural log of the concentration versus time. And it should give us a straight line plot if this reaction is in fact a first order reaction. All right, so we're going to again plot the natural log of the concentration of A versus time, and hopefully we'll see a straight line. So this is an example from your textbook, so luckily they already plotted this data for us. So again, on the y-axis, you can see that they've plotted the natural log of the concentration of the reactant. And on the x-axis, they have time. And we do get a straight line plot. And then the equation for the line is also shown. And remember, we want to prove that this is a first order reaction. And by graphing the data this way, we have shown that it is first order because we get a straight line. But additionally, we need to find the value of K, the rate constant. So remember that the slope, M, is equal to negative K, which is negative 0.000290. So that means that our rate constant K is 0.000290. Now, what about our units for K? So that's always a little tricky. Let's go back to our summary table. So the units of K for a first order reaction is inverse seconds. So we can write that next to our value of K. All right, not too bad, right? Especially when they plot the graph for you. All right, so now in the second example in your textbook, it says that in example 14.3, you determined that the decomposition of SO2Cl2 is first order and has a rate constant of 2.9 times 10 to the negative fourth inverse seconds. If the reaction is carried out at the same temperature, and the initial concentration of the reactant is 0.0225 moles per liter, what is the concentration after 865 seconds? Okay, so this is a first order reaction, so let's write out the integrated rate law for a first order reaction. And instead of the concentration of A, I'm going to write the concentration of SO2Cl2, since that is our reactant. Okay, so this is our integrated rate law for a first order reaction. And we already determined that this is a first order reaction. We also already determined the value of K. So we have K, we have the initial concentration of our reactant, and we have the amount of time that the reaction is going to run. So we can plug all of those into our equation. So we'll plug in the rate constant, and we'll also plug in the time, which was 865 seconds. And then we'll also plug in the initial concentration of the reactant. Okay. So when we do this calculation, we should have a value of negative 0.251 minus 3.79. And all of the units here should cancel out, or, just disappear. So we should get, except for moles per liter. And this should give us an overall value of negative 4.04. Okay, and remember this is equal to the natural log of the concentration of our reactant. So in order to solve for just the concentration, we're going to need to take the inverse natural log of both sides. So that would be e to the negative 4.04. And that would give us a value of 0.0176 moles per liter. So that is our concentration for our reactant after 865 seconds. Okay, so hopefully this example shows how we can use integrated rate laws to determine the concentration of our reactant after a certain amount of time, and then we could potentially relate that to the amount of product that should form as well. All right, so let's go over one more example here, and then we'll work on a worksheet problem. So consider the equation for the decomposition of NO2. The concentration of NO2 is monitored at a fixed temperature as a function of time during the decomposition reaction, and the data tabulated in the margin at right. Show by graphical analysis that the reaction is not first order and that it is second order, and then determine the rate constant for the reaction. So luckily for us, they already graphed the data, and remember, we want to prove that this reaction is not first order. So what we'll do first is plot the natural log of NO2 versus time. And hopefully we'll see that this does not give us a straight line graph. And then second, we'll plot 1 over the concentration of NO2 versus time. And we should get a straight line there, because this would occur for a second order reaction. All right, so this is our plot of the natural log of NO2 versus time. And you can see that it is not a straight line plot. So we actually have a bit of a curve here in the data. So we don't have a straight line. So this is not a first order reaction. So now let's plot 1 over the concentration of NO2 versus time. And we get a straight line plot like we would expect for a second order reaction. All right. Now the other thing we needed to do here was determine the rate constant. So remember, for a second order reaction, the slope, which is m, is equal to k, and in this case, that's equal to 0.255. Now, what about the units for this rate constant? Let's actually go back to our summary table, and for a second order reaction, the units are inverse moles per liter and times inverse seconds. All right, so we can write that next to our rate constant. All right, so you can also use what we know about these different orders of reaction to prove that something is not a particular order as well. All right, so finally, the worksheet problem, problem 4. And then this will be the last thing we do for this lecture. It's a bit of a long one, I apologize. So the reaction was monitored as a function of time, where a reactant, AB, is decomposing, and a plot of 1 over the concentration of AB versus time yields a straight line with a slope of 0.55 moles or inverse moles per liter per second. What is the value of the rate constant? A. B. Write the rate law. C. What is the half-life when the initial concentration is 0.55 moles per liter? And D. If the initial concentration of AB is 0.25 moles per liter and the reaction mixture initially contains no products, what are the concentrations of A and B after 75 seconds? Okay, so if you do want to try this on your own, feel free to pause the video. Now let's start with A. What is the value of the rate constant for this reaction at this temperature? All right, so we should probably figure out if this is a 0 order, first order, or second order reaction first, because that can have an effect on the rate constant. So if a plot of 1 over the concentration versus time yields a straight line, is this reaction 0, first, or second order? So it is second order. And remember that in a second order reaction, we actually have a positive slope. So it looks something like that. So remember, the slope will equal K, which in this case is 0.55 inverse moles per liters per second. Okay. Now for part B, write the rate law for the reaction. So this isn't the integrated rate law, this is just the regular rate law. So this would equal the rate constant times the concentration of the reactant squared, because we determined that this was a second order reaction. But we also said that the rate constant is 0.55 inverse moles times inverse seconds, or moles per liter per second. And then we'll just multiply that by the concentration of the reactant squared. So not too bad. And now for C, what is the half-life when the initial concentration is 0.55 moles per liter? So earlier we said that the half-life expression for a second order reaction is T1/2 equals 1 over the rate constant times the initial concentration of the reactant. All right, so we already said that the rate constant is 0.55 inverse moles per liters per second. And we're told that the initial concentration is 0.55 moles per liter. Okay, so if we calculate this, it's 1 over 0.55 times 0.55. So that should give us, let's see, what did I get? So I got 1 over 0.3025, and let's see, what are our units? So moles per liter will cancel, and we're just left with inverse seconds. So I'll just write seconds to the -1 in the denominator. And then that should give us 3.3 seconds. All right, so the half-life for this reaction is 3.3 seconds. But remember, second order reactions do have a dependence on the initial concentration of their reactant for the half-life. So if the half-life does depend on the initial concentration, in this very particular instance where the initial concentration is 0.55, the half-life is 3.3 seconds, but that could change depending on the initial concentration. So just keep that in mind. And finally, D, if the initial concentration of AB is 0.25 moles per liter and the reaction mixture initially contains no products, what are the concentrations of A and B after 75 seconds? Okay, so let's use our integrated rate law for this problem. Now, the reason I'm using the integrated rate law is because we're trying to determine how much of the reactant is left after a certain amount of time. So we're given the initial concentration, we know how long the reaction is running, and we also know the initial concentration of the reaction. So because this is a second order reaction, we're going to use the integrated rate law for a second order reaction. And then we're just going to plug in what we know. So K, we already said, was 0.55. And then the time is 75 seconds. And the initial concentration of the reactant is 0.250 moles per liter. Okay. So we should end up with 45.25, and then let's figure out what our units are here. So if we look up above, we have, so seconds and seconds cancel, and then we just have inverse molarity for both expressions. Now remember, this is equal to the 1 over the concentration of the reactant. So we actually need to rearrange some things to solve for the concentration of AB. So the concentration of AB will be 1 over 45.25 moles per liter. So that should give us a value of 0.022 moles per liter. All right, so keeping track of units is really important for these types of problems. And I know this lecture was a bit longer, but hopefully this helped you to kind of see where these integrated rate laws are coming from and then why they're useful. So remember, we can plot data in different ways to try to determine the order of a reaction. And then once we narrow down what the order of the reaction is, we can also figure out what the rate constant is from the slope. But we can also use these integrated rate laws to figure out concentrations of reactants or products at particular time points in a reaction. So there are a lot of different ways we can use these particular equations. All right, so I'll let you go and I will see you in the next video.